All right, so then you're going to have a lower bound. You're going to have an upper bound. You're going to have a mean, and you're going to have a standard deviation, right? We know that. That's chapter 6 and chapter 7. These are especially convenient if you have standard normal, right? That's with Z's. Because if you have standard normal, it means that your mean is 0, and it means that your standard deviation is 1, which is especially nice. Now, if you don't have standard normal and you have just normal, if you have X, then those can be anything. But we know that. That was all of chapter 6. And then, of course, there's the opposite way of in case you need to find the area under the curve given your bounds, right? Okay, so this was chapter 6. That's what we did. Okay, let's talk about chapter 7 then. Make sure this is focused. The stupid automatic focus is a lie. Okay, here we go. Now, chapter 7, we're doing the same thing. Remember, we have a lower bound. We have an upper bound. But this time we're doing sampling distribution. So we're taking a bunch of different samples out of the population. Then we're finding the mean of those samples and the standard deviation of those samples. Well, it turns out for chapter 7 that your mean is just your mean, right? You're still going to use whatever mean they give you, whatever mean they give you. The difference in chapter 7 is they give you N, right? They give you N, that's sample size. That's the difference in chapter 7. That's it. If you don't see a sample size, don't worry about it. You're up here. Use the standard deviation they give you. If they give you a sample size, then you're going to use it to find sigma x bar. This guy is going to be the regular standard deviation over the square root of N. That's the difference in chapter 7, and that's it, right? That's what we talked about. That's all you got to do, okay? All right, now here's what we're going to learn that's different. Oh, and by the way, this was all dependent on your sample size being equal to or greater than 30, which we said it always is in this class, so we don't have to worry about it. Okay, now we are going to start, okay, where it says section 7.5, 7.6, right? We're going to start with proportions. That's what we're going to do today, is just finish that up. And then you got a couple of additional problems. Okay, the difference now is that you are going to have either the word proportion or you're going to see a percent. Okay, you don't have to write this down because we're going to go through it on here, but I'm just going to kind of give you the nitty gritty and then we'll talk about it on here, but it's up to you. Okay, now you're going to either see the word proportion or you're going to see a percent. Okay, so you are still going to have a lower bound. You're still going to have an upper bound. That hasn't changed at all. But when it's time for you to find the mean is going to be P, or the percent, but you're going to change it to a decimal. Okay, we're going to go over all this and talk about it. But so now the difference is you're going to either see a percent or hear about proportion. So your mean is going to be that. You will no longer see the word mean. You will no longer see a mu, but the percent that they give you, change it to a decimal, that's your mean. Okay. Also, you're now going to get a standard deviation of p hat. What in the world is p hat? We're going to talk about that in a minute. It's the same thing as x bar, only just for proportions. Okay, so to find this guy, remember this guy was sigma over square root of n. This guy is going to be square root of p times q over n. That's what we're going to put in for him. Other than that, it's the same. Okay, so we know our P. Anybody remember how to find Q? He's 1 minus P. Remember him? And then the N. And we put it in. That's it. That's all we're going to cover now. Is that we're now going to talk about proportions or percents, same thing. And these are the formulas we're going to use instead. So your mean is now your percent. Your standard deviation is now going to be this crazy little formula. That's what you're going to use anytime you see a percent or a proportion. Okay. All right. So let's jump right in then. So here we are. We're going to start right here. This, of course, has to go through and tell you every living thing. We'll talk about it, but you don't have to know all of this because you're not going to be using a lot of these crazy formulas. You're going to use your calculator, but it doesn't hurt for you to know what they're talking about. Okay. All right. So these two little formulas are going to come up on Wiley. So you might just want to be prepared. They're going to show up for your Wiley homework and your Wiley quiz. Other than that, you really don't see them again. But what this tells you is that P is the population proportion. It's also the percent as a decimal. I'm just going to throw that in so we don't forget that little fact. Okay. But he's the population proportion. So big X is the number of elements in a population that have some characteristic. Maybe everybody with brown hair. Maybe everyone who's left-handed, right? Something like that. And capital N is the total number in the population. So if I wanted to know the proportion of blondes in this class, okay, and we pretended this was a population, I've got 3 of you, right? Oh, well, you do a little blondish. You're the new, what do they call that? Where they do brown and blonde together. It's like a word now, but I can't think of what it is. It's not brown. It's like the other way. Blonde or something. Anyway, all right, we're going to call you brown. Anyway, so there would be 3 would be the top number, right? And then capital N would be everybody, the total number of everyone in here. So we know how to find that. Okay, little p hat. What in the world is p hat? P hat is just your random variable for this. Okay, it's like X bar. It represents your sampling distribution. That's all it does. So anytime you're talking about proportion or percents, you're using p hat. That's that little what do we call that, caret that's sitting on top of p, they call it a hat. So that's p hat, and he's just like X bar. Okay. Anytime plain p is involved, it's a population. Anytime p hat is involved, it's a sample. That's how you know the difference. Okay. So population, because it's plain p, p hat, because it's a sample. All right. So if we had just a sample of this group, maybe just the girls, and I wanted to know, brown haired from the girls, then I would pick brown haired girls on top, total number girls on bottom, right? And that would be what that means. Okay. And then don't forget this little Q equals 1 minus P. So as we start to review on Thursday, make sure, and I laid more key formula sheets out there in case you want a fresh one for chapter 6 and 7 for test 3. This may be one of those things you want to write on there in case you forget that, because it's not on your formula sheet. Okay, so also remember, we're using the CLT. The central limit theorem is what tells us all these formulas are valid, right? So we could use, what do I do with it? We could use this stuff from chapter 7 because this is what the central limit theorem required, right? It just required your sample size was greater than or equal to 30. With proportions or percents, it's going to require that n times p is greater than 5 and n times q is greater than 5. So Wiley is going to make you test this. They're going to say, can you use the central limit theorem? And you're going to have to take n times p and see if that's bigger than 5, and n times q and see if that's bigger than 5. If even one of those doesn't work, can't use it. Okay. All right. We already talked about this. We said that the mean for proportions and percents is just going to be p. Right? You're going to have to change it to a decimal, but it's just going to be p. We also talked about this. We said our new standard deviation is going to be the square root of p times q over n. Okay. And then, of course, this is still in play, but you don't have to remember that because it's always going to be valid. It's just get used to seeing it at the end of every problem. Okay. All right. And then for some reason, if they wanted you to standardize it, okay, this is for standardizing. If they wanted you to standardize it, or they wanted you to find the Z value, then here's your formula for Z. It's going to be P hat, that'll be given to you in the problem, minus your percent, you're going to turn it to a decimal, divided by this guy on the bottom. Okay, that would be how you use that if you need it. All right. So that is the rest of all your new information. And we're just going to do some problems, okay, and kind of work it all out. So here we go. So I'm trying to kind of let you see that it's, even though there's a lot going on, it's all the same thing. There's just little bitty changes. That's it, but they're not that bad. Okay, so first example, can the CLT be applied to describe the sampling distribution of the following? So all you have to write is yes or no. Well, that means either n has to be greater than or equal to 30 if we're dealing with X bar, or that these two have to be true if we're dealing with P. Just so happens we're dealing with P. So we're going to have to multiply N and P together and see if it's bigger than 5. Then we're going to find Q and multiply N and Q together and see if it's bigger than 5. If both of them are true, we write yes. So here we go. Okay, first thing we're going to do is N times P. So 43 times 0.45. Let's see, I came up with 19.35. Well, that's definitely bigger than 5, so that one's true. Okay, now I'm going to have to also find N times Q. Okay, so remember, Q is going to be 1 minus 0.5, so that's 0.55. So now I'm going to do 43 times 0.55, which is 23.65. So, yep, we can apply the CLT to that situation. Easy enough. Okay, let's try the next one. Okay, here my N is 7, my P is 0.3. Okay, we multiply N times P. Oh, I got 2.1. That's less than 5. So I can automatically put no. I don't even have to try the Q. But if you wanted to, what would my Q be if my P is 0.3? 0.7, right? Q is just going to be 1 minus 0.3. Okay, that one actually gives me 4.9. Is 4.9 less than 5? Yeah, so it's still no. So either one would have been no, but one of them being no is enough to say no, stop. Okay, so there you go. All right, let's do some actual problems now. All right, here we go. So example says, suppose that the true proportion, that's P, of Americans over 25 years old that have a 4-year college degree is 35%. All right, notice they didn't put 35 with the little percent symbol, right? So you're going to actually have to read the words so that you figure out what it is. Okay, now we want P and we want Q. P is not going to be 35 because hopefully you guys know at this point you can't ever use a percent for anything. What am I going to do to 35% so I can use it? Make it a decimal, divide it by 100, move it 2 places to the left, all the above. So now we're talking P is 0.35. Okay, so remember, not only is that P, what else is this equal to? That's our mean. So when it comes down to it, we have our mean also. Okay, so I'm just going to throw that in there. That's also our mean. All right, now we need Q. So Q is going to be 1 minus 0.35. So that's 0.65. All right, now we have 2 little parts of the question that we want to answer. So part A, find the mean and standard deviation of the sample proportion for the samples below. Okay, so first thing they want is if our sample is 38, what's the mean? Well, does the sample size have anything to do with the mean? No, we know what our mean is. It's 0.35. It's going to be 0.35 no matter what the sample size is. The sample size controls the standard deviation. That's the situation, right? Okay, so Now to find this, we're going to use that formula, square root of P times Q over N. Okay, so our P is 0.35, our Q is 0.65, and we're going to divide by 38. Okay, we're going to take the square root of that whole thing. And what did I get? I got 0.0774. Make sure that's right, because you know I come up with weird stuff sometimes. Okay. That would be my standard deviation. Does that sound okay, Kate? Okay. All right. Let's try the next one. Now our sample size increases. Now we're up to 75. Does that change our mean? Nope. Mean is P every time. It doesn't matter what your N is. Okay. So now let's try another standard deviation. Okay. The only thing different about this one is going to be the denominator, right? It's still 0.35 times 0.65, but now we're dividing by 75. And we're going to take the square root. I came up with 0.0551. Okay. All right. So again, just to kind of let you think about that, is that the larger the sample size, the smaller the standard deviation, which is how it should always work anyway. Okay. All right. Let's actually do a problem then. Okay. So now if a sample of 75 Americans, okay, that was the last one we did, so we can actually just swipe the info from that guy, over 25 years old is randomly drawn. Okay, don't get number happy on me. Are we going to put that 25 in anywhere? No, it's just describing the problem, but we're not going to throw that in. That's just telling you what we're looking at. Find the probability that over 40% of them hold 4-year degrees. Over 40% hold 4-year degrees. Okay, so we want the probability of that. When the probability is brought into it, this percentage is P hat. So notice what it's asking for right here. The probability that P hat is greater than 0.4. That's the same thing that this last sentence just said. The probability, that's capital P, that over 40% of them, that means greater than 0.4. Does everybody see how that translated into that, okay? So up here, this just gave you a standard percent, just a sentence, like a little factoid, a little fun fact. That's P for the whole proportion, for the whole, the whole population, okay? Then when they ask for the probability, that percent turns into P hat. That's the one where we're talking about the sampling distribution. That's where that came from. Is everybody okay seeing that equals that there? All right. Okay, so first thing we want to do is check, is NP greater than 5 and is NQ greater than 5? All right, well, N is 75. We know P is 0.35 and we know Q is 0.65. So if I do N times P, 75 times 0.35, I get 26.25. So yeah, that's bigger. And if I do NQ, that's 75 times 0.65, that's actually 48.75. So yeah, we're definitely good there. Okay. All right, we are ready for our probability then. So here we go. We can go to Normalcdf in our calculator. Anytime we do probability, we do that. Let's think about lower bound and upper bound, mean and standard deviation. Okay, so if I want to be greater than 0.4, what's my lower bound? 0.4, right? And then what's my upper bound? Positive infinity. Okay, what's my mean? 0.35, right? Because that was P. Remember, your mean is P. And then what's my standard deviation that I'm going to put in? Good, 0.0551. Okay, because we figured it out from here. All right, I don't have a calculator to throw that into, but what do you get when you do that? I think you get 0.1821 something. that sound right? And there's my answer. Okay, is everybody okay with where these numbers came from? Okay. Oh, nice. Oh, okay. So you're going to do normal CDF. Do you want me to do it on here? You sure? Okay, sorry. Yeah. Okay, that one is from the standard deviation that we came up with because the sample size was 75. Because I just stole it from there because we'd already done it. Yeah. So you'll do normal CDF, lower bound, upper bound, mean is P, standard deviation, make sure you use this little formula here. And since we'd already done it up there, I just grabbed it. Okay. That sound all right? Okay, let's try another one. Okay. This one will help us get it kind of all worked out of our system. Then we just have a couple of additional problems. Okay, so this is all put together here, the whole thing. It's not all spaced out weird. Okay, so according to a university study, I don't know why U is capitalized, 1/3 of Americans believe that the next 5 years will bring good times. Okay, so assume that 33% of the current population of Americans holds this opinion. So this 1/3 is the same as 33%. Oh, there's a little bird. Sorry. Got distracted. Hi. Oh, they all want to learn stuff. Sorry. All right, so 1/3, so that's 33%, okay, of the current population. So what does that translate into? What am I going to do to 33%? 0.33. And what's 0.33 going to be equal? What letter is 0.33? P. Good. So remember, it's like the first little factoid. That's giving you your population information. That's your P. You just have to change it to a decimal. And then it's always a good idea. As soon as you get P, you go ahead and tell Q. Because even if there's not a blank for it, you know you're going to need it. So what's Q going to be if my P is 0.33? Good, 0.67. That's right. 1 minus 0.33. Good. All right. Now we're going to keep reading. So let P be the proportion. That's actually supposed to be P hat. I'm sorry, guys. Put a little hat on him. My computer won't do that. I can't find that. Let P hat be the proportion of a random sample of 800 Americans who are asked their opinion on this issue. So what's 800? What's our N? Most of the time, you know, I hate to say all the time, but most of the time, like 99% of the time, they use proportions when you have a gigantic sample. So look at that sample size. We have never had anything in as 800, but that's when they usually use proportions, is when you have these giant sample sizes. Okay, so what bothers students about this kind of a problem is that's all the info it gave you. It gave you two things. It gave you P and it gave you N. And they're like, I know I have to have more numbers than that. No, you don't. That's all you need. That's really all you need. Okay, so we found Q. We know N. Okay, now part A wants to know, can we use these formulas? Is NP greater than 5 and is NQ greater than 5? So if I multiply 800 times 0.33, I come up with 264. So definitely yes. Then if I do 800 times 0.67, I come up with 536. So definitely yes. Okay. And then I notice over here, it wants one last thing. It wants me to go ahead and get my standard deviation handled. So remember, this is the standard deviation of P hat. So this is that standard deviation that looks like this, that you can't see there. Square root of PQ divided by N. So we're going to have the square root of 0.33 times 0.67 divided by 800. Okay. Should be 0.0166, something like that. You know if it's weird. Is that good? Okay. All right. So now, everybody go to part A. Okay, part B says, find the probability that the value of p hat is between 0.35 and 0.37. Well, you don't have to, but if you wanted to write this over like a nice little inequality, you could. That's what that means if you wanted to write it. Okay, so if I go down here to B, now remember, we're going to normal CDF anytime it asks for probability. That's where we're headed. So if it wants a probability, this is the info we're going to need for our normal CDF. So for B, what's my lower bound? Happens to be 0.35. My upper bound, 0.37. What's my mean going to be? 0.33. Good. We didn't label it, but remember, P is your mean. So as soon as you get it, you may want to label that too, because your brain will forget it. And then we already found our standard deviation. There we go. And when we put all that in, what did I get? I came out with 0.1071. So 0.01061 or 62, something like that. Okay. That's pretty off. Sorry about that. Okay. All right, let's look at C now. I'm way down here and do him. Okay, part C wants find the probability. So again, if you want to make yourself a little inequality, you can, that less than 30% of the sample has this opinion. Okay, so again, now we're dealing with p hat, less than 30%, so less than 0.3. Okay, that's now what our new probability is. Okay, so again, we need a lower bound, an upper bound, a mean, and a standard deviation. Okay, all right, so based on this, what's my lower bound going to be? Should be negative infinity, right? Because less than 0.3, that's my lower bound. Then what's my upper bound going to be? 0.3. Is everybody okay with those lower bound and upper bounds? Okay. All right. Then our mean stays the same and our standard deviation stays the same. That doesn't change. Okay, what did we get for C? I'm scared to tell you what I got. I got 0.0354. Yeah, maybe. Okay. Okay, close enough. All right. And now we have part D. Okay, we want the probability that p hat is greater than 38%. Oh, look what they did to you. They threw a percent in there. They can't do that. All right, I've got to change that to the probability that p hat's greater than 0.38. Okay, so lower bound, upper bound, mean, standard deviation. Okay, so if I want to be greater than 0.38, my lower bound is 0.38, and my upper bound is infinity. Mean doesn't change, standard deviation doesn't change. Okay, how about 0.0013? Yay, okay, all right. So now you kind of understand, anytime you have those huge sample numbers, that's kind of, then we start switching over to percents or proportions, and that's how we handle it, okay? So chapter 6 and chapter 7, they're grouped together because it's lower bound, upper bound, mean, standard deviation. That's it. Then the only thing that really changes is your standard deviation, depending on which situation you have. Okay, does that sound all right? Okay, so then that takes us to additional problems. Now we already did this one. Remember we talked about the electricity situation, how they have to kind of plan ahead for kilowatts. This one was weird because it said it was within $6. So our lower bound and upper bound, we had to take our mean and subtract it and add the 6 and kind of go from there. Okay, so let's look at number 2. Okay, so number 2 says, you have a population of 95 subjects. Well, that's interesting because we usually have a sample size. Now we have a population size. So this is actually going to be big N, okay, not little n. Then it tells us 76% possess a certain characteristic, okay? So I'm talking about population, I'm talking about percents of a certain characteristic. That's when we have to go back and get those weird formulas we talked about. Remember those two that I said would come up on Wiley? Here it is. That's the first one. That deals with population, okay? So then, if we keep reading, it says in a sample of 400. Now I know that's ridiculous because if there's only 95 in the population, how can you take a sample out of that that's 400? Just, I don't know what I was thinking. Just go with it. Let's just pretend that it's a different population. All right, 78% possess that. Okay, so remember, that's where little p hat comes into play with little x over little n. Those are those two formulas we talked about. Okay, then they're going to want to know how many subjects possess the characteristic. So what they want you to solve for is big X and little x for each one, for the population and the proportion. That's all they're wanting you to do, okay? So if we go up here and do the population first, this is P. We just have to change it to a decimal. We don't know X, but we know that it's over 95. And now we're just going to solve for X. Okay, so remember, you can either multiply both sides by 95, and this cancels out, or you can just shoot it over there and multiply it, whatever you're comfortable doing. I think they want you, I'm not really sure. If they want decimals, you would do this. If they want just whole numbers, you're going to have to round it to 73 because we talked about the fact that if you have subjects, that means that that's some kind of whole number. It's bags of something, it's animals, it's people. You can't have 0.20. So if they ask you specifically for two decimal places, use this. If they just ask you for the number of subjects, they want a whole number, you have to round up. In statistics, you always round up to the next whole number. Okay, then for this guy, because it says it's a sample, this little guy's p hat. So we're going to do 0.78 equals little x over 400. Same math, we're just multiplying those together. I think that one comes out even, 312. Okay. So not a test problem, just a Wiley problem. All right, number 3 is also just a Wiley problem. And because you have been doing all this complicated stuff, you probably can't figure out how in the world to do number 3 because it's just so easy. If you were back in chapter 1 and 2 and 3, you'd knock this out. But now that you know all this fancy stuff, you can't do the easy stuff. So it's going to give you some numbers. It wants you to write the population distribution. Don't get freaked out. All this means is you're going to make one of these guys. You did this all over the place before and we're just fine. Okay, so first thing we're going to do is write what numbers we have. I have a 3, I have a 7, I have an 11, I already have 7, so I don't need him again, and I have 19. Okay, now all we want is the probability of that. Okay, so remember, at its core, what does this mean? There's 1 3 out of how many numbers? 5. And then this is just going to be 0.2. That's his population distribution or his probability. Your n is 5. Okay. Now 7 is going to be a little different because how many 7s do you have? 2 out of 5 numbers. So he's actually going to be 0.4. You only have 111 and you only have 119. And then remember, just like we thought, if we add all these together, they equal 1. So we're good. So this is your population distribution or your probability distribution for this population. It's that easy, so don't overthink it. Yeah. Okay. Uh-huh. Oh. Yes. So let me see what you got. Oh, not three. They count, oh, so you only have 1, 2, 3. Okay, so you have 5 numbers, but you have 2, 3. So you're gonna have 2 divided by. That's okay. You're welcome. Okay. All right, everybody good? Okay. All right, brings us to our last one. Okay. Now this one's very easy, except that it gives you extra information. And I know anytime you get something extra, you're going to put it somewhere, right? Even if it's somewhere weird. So we got to make sure you're comfortable. All right, so this says for population n equals 10,000, our mean is 132, sigma is 17. Find the z value for x bar equals this for a little n at 25. Oh my gosh. Okay, so first of all, it wants you to find z. We haven't had to find the z value in a really long time because why? We don't standardize. We put it right in our calculator. Okay. Also, because they're giving you x bar, this is not from the proportion section, right? This is from way back at the beginning. So if you go back and look for your z formula dealing with x bar, this is where we are. This is what it wants. So it wants x bar minus the mean over the standard deviation of x bar. That's your situation. Now, we have x bar. We even have the mean. Be careful. Do we have sigma x bar though? We don't. We only have plain old sigma. Remember, if they give you an n, if they give you a sample size, that means you have to find sigma x bar. That's the difference in chapter 6 and chapter 7. If they give you a sample size, you have to use it. So what's our extra piece of information? This. We don't care how big the population is. We're not going to use it. That's extra info. So don't let Wiley throw you off on that. Okay. All right. So remember, this is just going to be the standard deviation divided by the square root of n. Okay. So we're going to have 17 divided by the square root of 25. Get that somewhere. Which is 3.4. Okay. And our z is going to come out to be 0.70. That's all it wants for this problem. Okay. So Wiley throws some weird stuff at you. That's not going to be on your test. Your test is mostly just lower bound, upper bound, mean, standard deviation. But there you go. So remember, if you see a sample size, you have to use it to change your standard deviation. Other than that, that's it. Okay, that's everything. If you guys want to do any Wiley and go over it, you certainly can. We'll review on Thursday.